Okay, in this video, I want to talk about the karst aquifers in the eastern U.S. And this is going to be principally the Floridan aquifer here, and then the Paleozoic aquifers in the mid-continent. And they'll be in this area here. So we'll first look at large-scale structural controls on these aquifers, some conceptual models and aquifer properties, water quality, and then some unusual aspects of geomorphology and biodiversity associated with karst aquifers. So the structural features of the eastern mid-continent are shown here. This is the Appalachians right here, this dotted line, and then there are some gentle troughs and ridges with basins and domes along these features. And what I'm showing here are the axis of these features. The first one going to the west of the Appalachians is the Appalachian Basin. There. So Appalachian Basin. And then the next one is the Findlay Arch and the Cincinnati Arch. That's right there. And along that arch, there's a dome right here. That's the Lexington Dome, and the Nashville Dome is right there. And then the next structural feature is this low lying area, and right along here, this is the Mississippi embayment. And then right in here is the Illinois Basin, and this is the Michigan Basin. And then the next structural feature is this guy here. This is a structural high, and this is the Wisconsin Arch here and the Ozark Plateau. And then there's also another structural high that's out here, more or less. That's the Transcontinental Arch. But these are the features of the mid-continent that'll control the location of the aquifers, the karst aquifers in the mid-continent, because these structural features, even though the rocks are really gently dipping in this area, these structural features control what rocks are exposed. So you can see that these features it's kind of like a fold train here. If we look at it in cross section. So we've got the Appalachians right here, and then we've got the Appalachian Basin is a trough, and then we've got this ridge right in here. And then we've got this low-lying area here with the Mississippi embayment and these two basins, and then this ridge. So we can. This is kind of a simple way of keeping track of where those major structural features are. So there's some of the names, and there you go. And so what would be useful is for you to go ahead and see if you can name what these features are just from memory. That'd be good exercise. One thing that's also useful is that there are features going along this axis. So this is the Savannah River Basin right along here. And if we go along this axis, this is also a structural low in between these two domes and going up here into the Illinois Basin. And then we've got a ridge. This is the Cape Fear Arch right in here. And this is also a structural high going up in that direction. And then this is also a structural high here, the Ocala Arch here where Florida is, and then extends up here to the Ozark Plateau. So I'm not really saying those are structural features per se, but it is kind of an alignment of features of relatively high and relatively low lying areas. So that helps put all of these features in context. And what we see then is that this is a map of the major karst aquifers in the U.S., just a simple stylized map. And you can, and the alignment of these, or the appearance of these features and the structural features is going to end up being quite important. The Ocala uplift here along Florida, that makes this a structurally high area, and it's why we have land, and was also why there were reefs that persisted throughout the tertiary when these rocks were deposited. There are karst aquifers here in the Appalachians, and then there's this the structural high, and there are Ordovician aquifers exposed right here at the center of the Lexington and Nashville domes. And then the Mississippian aquifers shown here wrap around that high, and they also wrap around the low here, that's the Illinois basin. The Ordovician aquifers, Ordovician limestones here are exposed in the Ozark Plateau, where the rocks are uplifted, and so you have these older rocks exposed at the center of the dome. And the Silurian, it's wrapping around the Michigan basin here, and up here between the kind of on the edge of the Illinois basin. And then out west, we've got some additional karst aquifers filling these small basins. This is the Edwards Aquifer right down here. And then out west, we've got there's another Mississippian aquifer here. This is the Madison limestone, and then there are a variety of limestones here in the basin range. So here you can see those different features lined up with the structural features that I mentioned. And so you can kind of see the relationships between the two. Okay, so what I want to do is take a look at these Paleozoic karsts in the mid-continent, and you can see that they're shown here a little bit in a little better detail. These are the Paleozoic karsts at the center of the domes, and then the purple is the Mississippian. This is the brown is the Silurian. This is Ordovician here in the Ozark Plateau. And we'll also look at the Floridan aquifer system. So these are the two major karsts in the eastern U.S., and they're really quite different. The Floridan is tertiary and consists of very highly porous material, limestones, whereas the Paleozoic karsts are obviously Paleozoic, and the rock type is generally much lower porosity and permeability than the Floridan. So here's a cross section along the axis of the Florida. You can see here's the Florida Georgia border. So the Floridan aquifer is actually extending up into Georgia, and there are two main aquifers or karst units. This lower one here, this is the lower Floridan aquifer. The boulder zone down here, the scale there's 3,000 feet. So this boulder zone, this is down in very saline water. So this isn't really an aquifer containing fresh water, but this is a zone that's important in Florida because it's karst zone that has very high porosity and is used for waste disposal. The upper Floridan aquifer, that's this one shown here, and that's an aquifer that extends along the length of Florida, and these two aquifers are merging together up here in northern Florida. And then there's also a superficial aquifer, and the Biscayne aquifer, which is just a thin sliver up here, is an important aquifer, karst aquifer in southern Florida. And then these guys here are confining units between these different aquifer units. So you can see from this that at least along this section, this upper Floridan aquifer is confined by these Miocene rocks. And that's true along the axis of Florida. This zone here becomes unconfined over in the western part of Florida. Okay, so the important components of the conceptual model consist of these different things: epikarst, dissolution channels, fractured limestone, and limestone. So here's some pictures of limestone. These are from the different types of Paleozoic limestones. Micrite, this is formed from a lime mud, very fine-grained and very low permeability. Fossiliferous limestone, this is got abundant fossils, and so the porosity and permeability of this material can be moderate to fairly high, depending on how much cement there is. And oolites are sand grain sized particles of formed from limestone that are cemented to form a limestone formed oolitic limestone. So those are materials from the Paleozoic. The limestone in Florida is a bit different. Well, it's a fossiliferous limestone, and it has much lower cement content in general. It was deposited in a reef that persisted for quite a long time along Ocala Arch, which is where Florida is. Here's a picture of the Floridan limestone in a quarry, and even from this distance, you can see the large pore structure in this limestone. And if you zoom in on this, you can see the pore structure from these fossils that are still essentially, this pore structure is the primary pores from when this limestone was deposited. The scale on this is, I don't know, this is maybe a tenth of a meter, something like that. So these pores here are probably on the order of centimeter scale size pores, very, very large pores, and a lot of them. So this is very highly porous and highly permeable material as a result. Here's a photo from the same quarry, and this guy is showing a solution feature. So right here, in addition to having high porosity and permeability primary during deposition, this material has also been dissolved, and the cavities have been enlarged, and you can kind of see that dissolution feature shown here. And of course, the dissolution features are going to be common at the ground surface in karst. Karst is formed from limestone, which is soluble in carbonic acid formed by interaction between water and CO2. And that results in very common dissolution features and a material called epikarst, which is highly dissolved limestone. So here's an example of a vertical conduit shaped feature in epikarst Here are some enlarged fractures, kind of linear, tabular conduits. And this is a picture from right here. This is a picture from Mammoth Cave, one of the road cuts in Mammoth Cave. And you can see this is a dissolution feature here. And then there are a variety of, if you get up closer, there are a variety of smaller scale dissolution features throughout the rock. Here are some fractures in the limestone that have been dissolved out a lot less than what we see up here. And all of these materials at shallow depth where you have extensive dissolution form karst, the epikarst, which is quite high permeability, and the storage, the ability to store the water can be reasonable, because what happens is that in epikarsts where the limestone basically what happens with epikarst is the calcium carbonate gets dissolved away, and the clay minerals, the low solubility fraction, gets left behind as a residual. So there are some clays that form soils on epikarst, and that material can store some water. I mean, in this slide here, any kind of residual soil has been removed, so you don't have to have that residuum present. But where you do, that will store some water. In this kind of material, the storage of water would be really quite small, and that'll end up being important because the ability to store water and then release it slowly will affect the base flow recessions of streams in karst settings. So you can see we might have some clays here in this residuum in this sinkhole, although a little hard to tell. Up here in Mammoth Cave, this is all solid limestone, but up here at the top there are going to be some residual soils. Okay, so dissolution is going to be important at shallow depths, but also down in the subsurface in karst areas. It'll be an important component of the hydrogeologic system. This is a picture of a quarry in the Paleozoic limestones in the mid-continent, and you can see that dissolution feature there. The limestone is being quarried. This is a micritic limestone, and micritic limestone ends up being very nice building material. The Empire State Building is built from that, for example. It's quite strong and quite easy to work with, but you do have places where it's been dissolved out here with these dissolution features. Here's another picture from one of these limestone quarries, and this shows a nice vertical fracture here. That as you follow that vertical fracture up, you can see that it's been enlarged and flares out, and up here it spans this fairly large area, but it necks down as you go down with depth, and ultimately it shrinks down to this fracture. And so this is a sinkhole up at the ground surface, and it's a dissolution feature that is formed on this vertical fracture. And you can see that there's another one here, and then this is this sinkhole, and another one here, and another one here. So they're spaced all along. There's probably another one right here out of the image. So they have somewhat of a regular spacing all along this face of this quarry. And of course, dissolution features in the subsurface form conduits Sometimes the conduits are big enough to get into. So you can see these folks here exploring this cave that's filled with water. And so this ends up being the pore system in karst aquifers. Quite a large pore system, at least large in some places. And I think fairly obviously this would sustain a very high flow. Okay, so for conceptual models, this is the conceptual model from Ralph Heath, and it shows that it shows that limestone is flat lying, and we see the sandstone, shale, limestone. That sequence of material is what we see from the transgression, from a typical transgression sequence. So this assemblage of rock types will be quite common. The dark bands here are fractures filled with salty water, and they're overlain by fractures with, like this one here, they're filled with fresh water. So we've got a zone right in here where above that we've got fresh water, and below that we've got salt water filling the pores. You can see in this sketch we've got these large conduits, some sinkholes up here, and this incised valley. And the fractures or the conduits are formed along bedding planes. So this guy here is a fairly flat-lying conduit that's been formed by dissolving out along a bedding plane. And then there are vertical features that follow these vertical fractures that are forming vertical conduits. So that's one perspective on a conceptual model. Here's a nice diagram from the Mammoth Cave area. And this shows these karst conduits, some of which are quite large. And it also, I think it gives a little bit more detail on the perspective that we saw previously, where there are some conduits like this one that are following along bedding plane, and then this one is following perhaps a bedding plane that's overlying, and it has somewhat irregular shape, can be quite large or smaller. And then there are also vertical conduits or shafts here that are underlying a sinkhole. So these vertical conduits, they're going to be along a fracture, but what happens is that there'll be a preferential zone that forms. And so even though it's along a fracture, a long linear feature, there's a preferential zone that forms, and the dissolution is formed preferentially along one point or perhaps several points, but along an isolated limited length along that fracture, and that forms a vertical conduit. And you can see a variety of those vertical conduits here, and at the surface they're underlying these sinkholes, and that ends up being important because, and you can see this is shown here, the sinkholes form a direct conduit down into this flow system. And so it makes the flow system very vulnerable to contamination. So here's some groundwater contamination from a septic field that gets down into the aquifer through these vertical conduits. Another important aspect of these kinds of regions is a losing stream. So that's shown. You can see a little bit of it right here. And what happens is the stream is flowing along down this valley, and then it reaches this conduit. The water table is here, so it's flowing along this valley because it's flowing along some low permeability materials, and it's actually perched above the water table. But when it reaches this conduit, this could be quite a large conduit, and all the flow just simply goes down that conduit here. And so the flow, there's flow that goes along the stream valley until it reaches this place, and then all of the flow is suddenly lost and the valley is dry down gradient from there. This also shows kind of a nice feature here where back in the day, sinkholes were convenient places to dump trash. And so there are a lot of sinkholes that have undesirable materials in them that lead to contamination. So here's another conceptual model from Karst system. This is showing the kind of the development of a cave system where we've got some limestones that are dipping like this, and initially the piezometric surface looks like that, and then as the flow system, and you could imagine that at this point we would expect to have a flow system that kind of looks like this, and maybe something like this. And so early on, the flow would be through some small conduits like that, but we would then enlarge those conduits, and when they're enlarged, we're not going to be able to support the piezometric surface up here like this. When the conduits become enlarged, then the piezometric surface it may start like this, but as the conduits become enlarged and we have more permeable conduits forming, then this collapses, and now it looks like that. Okay, so we'll have this interaction between the development of the Karst dissolution and where that piezometric surface is. And so what happens then is that all of the dissolution that has taken place when this was saturated becomes abandoned, and that becomes then dry caves potentially that you could get into. And then here is what happens in some cases where fill is placed, so you no longer have water flowing down into this region right here, and then it uses this vertical conduit that was formed previously in an earlier stage. So that effect is also shown in this diagram. This is from the Marumath Cave area, and this is the discharge, the terminal discharge, the Green River down at Marumath Cave, and then the Pennyroyal Plateau are up here, and this is the plateau where Marumath Cave Lodge is. And what you find at Marumath Cave is that the streams and the upgradient area are flowing along, and they flow over some shales that are low solubility, and then there's a zone up along the region up gradient from Marumath Cave where the streams are sinking, and they go into the subsurface, and then there is a region where there is essentially no surface water. So the surface water goes in the subsurface and flows along like this, and then the water table is essentially at the base level of the Green River here, or close to it. And what has happened is that when the Green River was at a higher stage before it cut down to its current level, then the flow went and did this. And there was also infiltration that came and did this. But the flow system originally looked like that. and then the discharge stream point, the Green River, cut down, and this channel was abandoned. So that's the basic approach, and you end up with then vertical shafts, underlying sinkholes, and then horizontal fractures along bedding planes, some of which are enlarged. And then you also have a conduit system here that is submerged, and you would have flows something like this through that conduit system. So here's a cartoon that elaborates on that development of the Mammoth Cave area. Here's the Green River, and this is showing, well, there's some sinkholes here and infiltration and then flow along this conduit, and then there's down cutting of the stream. So in this in here, that would be right about at that point. Then it cuts down to here, and this set of horizontal conduits is abandoned, and now the flow goes like this. And then that happens again, and you've got a second set of abandoned horizontal conduits, and now the flow would go like that. And also importantly, the flow from up gradient goes like this. And then essentially you've got this kind of a, well, I guess you go from here, and the valley then gets partially filled, and this conduit here that's filled with water now is a result of the raise in the stage of the Green River from this low stage. So this part right here down at the lower extreme of the Mammoth Cave system was formed when the Green River was down a bit lower than it is today, and then it's been raised up by deposition of sediment. So that's thinking about how you have these multiple levels of conduits that are formed in the Mammoth Cave area. So to kind of put that together, the conceptual model for the limestone aquifers that, I mean, if we just have a flow system where the permeability is uniform, then we would expect to have a flow system that looks something like this, right? And so we don't, though. We have this area where the permeability can be enhanced by dissolution to a very large degree, and so that flow system ends up being modified by these conduits, but the overall dynamics still want to be somewhat like what we saw, except they're modified by the presence of these conduits. So you have the vertical shafts, the horizontal conduits. You also have significant springs that develop in karst areas, like I've shown here schematically, and that's a result of the discharge of these conduits that are, the discharge point is above the base level of the stream. So you've got these localized zones where you may have fairly high amounts of flow discharging out as a stream. Another thing that's important is that there are areas in karst systems, there are beds of relatively low solubility where you really don't have dissolution that's forming, not to any great degree, and those form confining layers, and I use the word confining here to mean to refer to confinement in the sense of transport. So these low permeability unfractured layers are barriers to contaminant transport from between this upper zone and the lower. And this is going to be important because the upper zone is highly vulnerable to contaminants because of this high permeability and low amounts of storage in the upper system, and because people are putting trash here in the sinkholes, or at least they used to. And so the upper part is very vulnerable to contamination, and that places a very important role on these confining units in the karst systems. So the properties, intact limestone, particularly these Paleozoic limestones, very low hydraulic conductivity, very low storage. And karstified limestone, where you have fractures that have been dissolved out, you can have very high hydraulic conductivities, but the overall storage, like a storativity, is still really pretty small. And that's because you may have some areas that have really big conduits, but overall the fraction of the area that has conduits is probably fairly small. But if they're big conduits, then on a regional basis you can have very high hydraulic conductivity, but it's not really storing a whole lot of water, and it's not, and out the water that does store drains out really readily. Now the epikarst, it can have fairly low hydraulic conductivity because you can have these residual clays, and if the residual clays are there, you can have relatively high storage of water in those residual clays. Just how much you would have would depend on how thick the residual clays were at that particular location. So here's some values of properties from a variety of sources. This is also from the book by Bill Back. And so this gives the porosity, hydraulic conductivity, and kind of an expected well yield. The yellow bars show some of the materials in the Paleozoic limestones. Well, actually, the yellow bars show some representative materials, not so much the Paleozoic, because we've got a oolitic limestone that's from the Paleozoic limestones, the mid-continent, but then Holocene coral limestones, that would be like the Biscayne Aquifer down in southern Florida, and karstified limestones with caverns, that would be in really in any kind of a karst system. And so here's some representative values for porosity, and you can see these porosities are fairly typical of other porous media, and the range for oolitic limestone, it can be very low if it's well cemented. Coral limestones could be quite high, and same with karstified limestones could be quite high. And so for hydraulic conductivity, let's see, that says 10 to the minus 1 meters per day. So in class, we've been using meters per second. So the conversion is that 1 meter per day is about 10 to the minus 5 meters per second. So that would be about 10 to the minus 6 meters per second for an average. That's 10 to the third. So that would be about 10 to the minus 2. And that's 10 to the fifth. So that would be 10 to the minus 2. And that would be 10. I guess that would be just equal to 1 meter per second. So remember, when we looked at the alluvial aquifers, we saw 10 to the minus 3, 10 to the minus 4 meters per second was a typical value for, let's say, 10 to the minus 3 to 10 to the minus 4, kind of at meters per second. Typical value for good productive alluvial aquifers. And so you can see the oolitic limestones is lower than that, although these Holocene, the coral limestones are a bit higher, and the karstified limestones are are quite a bit higher, 1,000 times higher or more. And so those are the average values. And we can see if we look at the ranges that the ranges are one or two orders of magnitude above and below the averages. So quite a broad range of possible materials or possible material properties. So here's an average of that. So for the hydraulic connectivity, the average for the Floridan would be about that, which is one or two higher orders of magnitude higher than what we were seeing for the alluvial aquifers. And transmissivity, some of these aquifers can be fairly thick, so we get 1,000 to 100,000 meters squared per day for transmissivity, and well yields can be really quite high, 20,000 gallons per minute. And you could imagine that, it's fairly easy to imagine how you get very high well yields if you have a well that intersects one of those large conduits.